graphs may appear to be different. If you draw them or if you choose certain labels for them, they may look different, but they might be actually the same, and that's established through relabelings of the vertices and comparing lists of edges. Right? So if that can be done, the two graphs are called isomorphic. And then one can try to classify different non-isomorphic graphs with a fixed number of vertices. So more concretely, one can create lists of all non-isomorphic simple graphs with a given number of vertices. For example, if the number of vertices is 1, and the graph is simple, there is only one graph, which looks like this, just a single lonely vertex. If the number of vertices is equal to 2, then you can either have two disconnected vertices, or you can connect them by a single edge. If the graph is simple, that's all you can do. Right? There are no multiple edges or loops. Number of vertices is equal to 3. Then we can have 3 isolated vertices, comma. So I'm writing these different graphs as a list. Or we can have a single edge and one vertex disconnected. Or we can have 2 edges. Or we can have 3 edges. And that's it. So there are 4 different simple graphs with 4 vertices. For 4 vertices, it's a more interesting list. So we start again with no edges at all. Then with one edge, it will always look like this: a pair with an edge and a pair without an edge. With 2 edges, it's already more interesting. You can have them like that, or you can link the 2 edges together and have one disconnected vertex. With 3 edges, you can have a triangle and an isolated vertex, or you can have the Mercedes sign, or so that's 3, or there's yet another possibility. You can link them up into one chain. Right, so these are 3 distinct possibilities with 3 edges. With 4 edges, well, clearly you can link them up into a square, or you can have a triangle with one additional protruding edge. So, okay, and you can check that that's all you can have with 4 edges and 4 vertices. 5 edges, you can have a diagonal, and that's the only thing which you can do. And with 6 edges, you can arrange them like this. Basically, with 6 edges, each vertex should be connected to each other vertex. You can draw it like that, right? When all of the pairs are connected up, you stop. You cannot have more edges. So it's a list with 11 different graphs. So 11 different simple graphs. And there are books in which this list, this classification, goes up to 20 or something vertices, around 20. And the number of different graphs, of course, grows. The more vertices you have, the more different and isomorphic graphs you can have. So it's only practical to have up to a certain point. So why am I only looking at simple graphs? That's because any of these simple graphs can be turned into a non-simple graph by simply multiplying any edge, which is already there. Just make it into a multiple edge, right? And also by adding loops to the vertices. And these are very simple modifications, right? Which you can put any number of loops on any given vertex, and you can multiply any edge which is already there to Hart's content. So these modifications are rather trivial, right? And obviously you can have infinite lists for each single graph here, right? You have an infinite number of such modifications because there's an infinite, arbitrary number of loops, an arbitrary number of multiplicities for each edge. So that's why it makes sense only to classify simple graphs, because they're like skeletons of any non-simple graph, right? So that's what I wanted to note in conjunction with isomorphisms, just to give you a flavor of what this gives to us, this idea of non-isomorphic graphs. Next thing I'd like to discuss is the degree of a vertex. So let V of G be the set of vertices of a graph G, and let V belongs to capital V of G be a particular vertex. The degree of V is a non-negative number, a non-negative integer, denoted as deg of V, that equals to the number of edges that have V as an endpoint. That equals to the number of edges, G, number of edges that have V as an endpoint. And also, so we should clarify what it means for a loop. A loop contributes, for a loop, each end of the loop contributes. For a loop, each end contributes. So therefore, a loop contributes summed of 2. Okay, so here's an example. I'll draw a graph, now discuss the degrees of various vertices. Okay, so it's A, C, D, touch to B, and this is an E. There's two loops. And there's also a vertex F, which is disconnected. So for this graph, the degree of F is 0, because it has no edges which end on it. The degree of C is equal to 4, because there are 4 edges which end on C. Degree of D is 1. And the degree of B is 4. So it has 2 ordinary edges, AB and CB, which end on it, and it has a loop. And for the loop, each end contributes. So you can think that if you cut a small circle around your vertex and just count the outgoing edges, that should give you the value of the degree. Right? So that gives you 4. Well, if you do the same procedure for the vertex E, right, restrict yourself to a small circle around the vertex and then count all the outgoing edges, that will give you 5, the degree of 5. The degree of E is equal to 5. So if you have a graph, you can find the degrees of all vertices, and it turns out that these numbers are not arbitrary. They all satisfy a number of interesting constraints. Perhaps the most famous constraint is the so-called handshaking lemma. I'll explain the name soon. The handshaking lemma theorem, which is really ancient stuff. So it was found by Swiss mathematician Euler in 18th century. So it says that if you, this lemma says that if you sum up the degrees of all vertices, the sum up of the degree of V, and in the sum, the V runs over all vertices of your graph, then that equals twice the number of edges. Right? So I put the vertical bars for the total number of edges. So why is it called the handshaking lemma? Well, imagine you have a room full of people, and they have been introduced to each other, and as they meet each other, they shake hands. So each person is supposed to represent a vertex in a graph, and each handshake represents a link or an edge between the two corresponding vertices. And then imagine that each person writes down the number of handshakes this person made, right? That's the degree of that person, of that vertex. So if you sum up all of the degrees, you get twice the number of handshakes, because each handshake contributes to the degree of 2 vertices. There's a little caveat, of course, that if we allow for loops, we should, in this analogy, we should be thinking about the person shaking hands with herself, and then presumably this person should record, the number of handshakes with the right hand and with the left hand, right? Then each self handshake will contribute 2, right? And then again, there will be only one link, but on the left-hand side, we'll have 2. Okay, so for that reason, we have a factor of 2 here, twice the number of handshakes that took place. Okay, that's twice the number of edges. So one simple illustration of this relation. So let's take a look at one concrete graph and see that it works. So let's look at the graph with 5 vertices, A, B, C, D, and E in the center. many edges we have here. We can count them. So there are 4 emanating from the center and 4 on the boundary, so it's 8 edges altogether. On the other hand, the degrees, so the degrees of A and B and C and D in the corners of the rectangle, they're all 3. Well, the degree of the point in the center, of the vertex in the center, is 4. So if we sum up all the degrees, okay, so that's sum over the degrees of V, that equals 3 times 4, that's the contribution from A, B, C, and D, plus 4. So that gives me 16, and that's exactly 2 times 8, right? 2 times the number of edges. So that's what it means. But it has more, this simple relation has more practical consequences. For example, if you don't know your graph exactly, but you have some constraints on what possible degrees you have there, then you can estimate, say, the maximal number of edges or the minimal number of edges this graph can have, or the maximal or minimal number of vertices, right? So this relation can be used to do some estimates. So let me illustrate this on a concrete example. The graph G has 53 edges and 5 vertices of degree 5. All other vertices have degree greater or equal than 7. All other vertices have degrees, we don't know exactly what they are, but all their degrees is greater or equal than 7. Based on the handshake lemma, what is the largest number of vertices this graph may have? Based on the handshaking lemma, what is the largest number of vertices this graph may have? Okay, so we start, of course, by just writing out all we can write in the handshaking lemma. So we're given the number of edges, so we know the right-hand side of the handshaking lemma. So the sum of the degrees on the left-hand side, I know some terms in it precisely. I know that there are 5 vertices of degree 5. So each of that vertices will be listed in the sum, and each will contribute a term which is equal to 5. So I have altogether 5 times 5, the contribution from those vertices. Plus I have, well, a contribution from the other vertices. So let me somehow change the summation notation. So let me put B prime for those remaining vertices. Just to, be careful, and not to write exactly the same sum of the degrees, right? So here, just prime means that the remaining vertices, which are not of the degree 5, and the whole thing equals twice the number of edges. We're told that there are 53 edges. So this sum should be equal to 2 times 53. That's as far as I can go, because I don't know these remaining terms precisely, but I know something about them. I know that all of these terms, each of them contributes a number greater or equal than 7. So where in the remaining sum, the degree of v prime is greater or equal than 7 for all of them. So I can write an inequality. So I have 5 times 5 plus that, oh, sorry, better create it up. Not to get, sorry, I usually go the far left. I'm continuing over here, so we can write an inequality, so I'm just going to copy this quantity, sum of the degrees of v dashed, so that we can certainly write that is equal to 2 times 53 minus 5 times 5, which is 25. And we know that each term here is greater or equal than 7. So this is greater or equal than 7 times the number, what's called n, the number of vertices whose degree is greater or equal than 7. Where n is the number of vertices with degree greater or equal than 7. I don't know that number, but I can write that the sum is greater or equal than 7 times n, right? Because each term, there are n terms in it, and each term contributes a degree greater or equal than 7. So what does this give me? It gives me an inequality 7n less or equal 106 minus 25. So it's 86 minus 5, that's 81. And therefore n is less or equal than 81 divided by 7. And that's approximately 11.57. All right, so the number of those vertices of degree greater or equal than 7 is less or equal than 11.57. But I know for sure it always has to be an integer. It cannot be equal precisely to this fractional number. Fractional number of vertices doesn't make any sense. So the largest integer which satisfies this inequality is 11. So based on the handshaking lemma, the largest possible number of those vertices with degree 7 is 11, and therefore the largest total number of vertices, right, is 5 plus 11, which is 16. So that's the answer to this question. Any questions, please? Yes. Sorry, what is 7? This 7, that's given here, right? So there are 5 vertices of degree 5, and there's also some other number of vertices. We don't know how many, but each of those has degree greater or equal than 7. Well, in this particular problem, it's 7. But yeah, it could be other, other information. Not a problem. Any other questions? So that's like really famous, the handshaking lemma, and one of its uses is this type of estimates. There will be more examples like this in the tutorial next week. So there's another interesting consequence. It doesn't have a name, but I'll derive that. So let's call it a fact. I don't even want to call it a theorem or anything else. It says that it's a fact that in a simple graph, or let's say in any simple graph, emphasize that, with the number of vertices at least 2, or greater or equal to 2, there are at least 2 vertices with the same degree. Right, you can look at the examples I've drawn before. Well, those were not simple graphs, but say the last one, the example above, it's a simple graph, right? And well, it has 4 vertices with the same degree. But this fact claims that it's always true in general. And the reasoning is kind of neat, so I'd like us to go through it. Proof. Well, since no multiple edges are allowed, the largest possible degree is the number of vertices minus 1. You can take one vertex and connect it to each other vertex, right? And that will give you the largest possible degree. Okay? So since no multiple edges aren't allowed, the largest possible degree in a simple graph is the number of vertices minus 1. All right, and the smallest possible degree is always 0, right? When you have a vertex not connected by any edge to another vertex. So we can create a list of all possible degrees. So all possible degrees, different degrees are 0, 1, 2, and so on, up to the largest possible value, which is the number of vertices minus 1. And with 0, you have here exactly as many values as you have vertices. So this is the number of vertices, so that's the number of possible values. So the only way to arrange for all degrees of your vertices to be different numbers is to use up each value from this list precisely once. Because there are this many vertices and this many possible degrees. But that's not possible in a simple graph because 0, the smallest value, and the largest value cannot appear in it together. Because if you have a vertex with that value, with the largest value, it means that it's connected to each other vertex. While if you get 0, that means that that particular vertex is not connected to any other vertex. So that's a contradiction. So therefore, it's not possible. But 0 and b minus 1 degrees cannot appear together. So at least 2 values from that list must be chosen to be the same. At least 2 chosen values must be the same. questions about this reasoning? It makes sense to everybody. Right. If everything is clear, then I'm going to move on. Now, talking to the next topic I want to discuss related to graphs is connectivity. So it's a whole set of issues really, but we'll be interested in seeing in how many ways two different vertices can be connected by a path, which is a sequence of edges in a graph. So it has some real practical value. So if you have a network, you really want to have a good idea of how well connected different sites in your network are. For example, if one connection breaks down, do you have an alternative connection? How many? If one connection breaks down, how many nodes will be disconnected, and so on. So we want to develop some terminology and also some ways of counting and quantifying connectivity in graphs. So let me start with some terminology. Two vertices are called adjacent if there is an edge, at least one edge, which links them. Two vertices, call them V and U, are called adjacent if there exists an edge associated, well, an edge, well, called E, associated with the pair VU, right? Or in simple terms, it just links this edge should link these two vertices together. Another definition, a path of length n from vertex A to vertex B is a sequence of edges satisfying a certain number of constraints. Let's write this down. A path of length from vertex A to vertex B is a sequence of n, which contains n edges, a sequence of n edges, which we can label as E1, E2, E3, E sub n, such that the first edge E1 is associated with a pair AV1. So A is the initial vertex from which we start out. A V1 is some intermediate vertex. Similarly, the next edge E2 is associated with a pair V1, V2. V2 is the next intermediate vertex in the path. And so on until the last edge E sub n, with which we are arriving at the final vertex B, is associated with Vn minus 1 B. So Vn minus 1 is the last intermediate vertex, right? And there are as many of them as the n minus 1. So here's a picture. A goes to V1, V1 goes to V2, V2 goes to V3, and then finally we arrive to V and minus 1 B. And this first edge is called E1, the second E2, the third E3, and the last is sub n. So n intermediate n edges corresponds to n minus 1 intermediate vertices. In a simple graph, a path can be represented by a sequence of vertices so that two neighboring vertices are adjacent, right? We don't need to introduce the labels for the edges because in a simple graph, there are no multiple edges. There's no need to distinguish them. They're just given by a pair of vertices. So in a simple graph, a path can be represented by a sequence of vertices instead of a sequence of edges. Sequence of vertices A, V1, V2, the dot, Vn minus 1, B, in which every pair of neighboring vertices is adjacent. More about paths. The path is called simple if it does not contain the same edge twice. A path is called simple if it does not contain the same edge twice. Here's an example. Let's consider a graph with 5 vertices, A, B, C, D, and E, and these connections. So in this graph, the sequence A, E, D, C, E is a simple path of length 4. So this is a simple path of length 4. 4 because we have 4, we can count the edges. There are 4 of them, and it's a path from A to E. If you reverse this sequence of vertices, of course it gives you a path from E to A, right? So far we're talking about ordinary graphs with no arrows, so undirected graphs with undirected paths. And well, I wrote it down, but of course, one should check that each pair of neighboring vertices is connected. Otherwise, it wouldn't represent a path at all. And indeed, you can see that we travel from A to E, from E to D, from D to C, and from C to E, and each time there is a connection there. But for example, the sequence E, C, B, A is not a path. Right? There is a connection from E to C, but there is no edge from C to B. Between C and B, there is no edge. So that's just a sequence of vertices, which is not a path. The first sequence I wrote is, I said it's a simple path, right? Which means you can check that no edge is used twice. Here's an example of a path which is not simple. B, E, C, E. This is a path length 3. There's 1, 2, 3 edges, and it is not simple. Not simple because the edge CE is used in it twice. CE is used twice. So we go from E to C and then we come back from C to E. So we use this edge twice. It's a path, but not simple. All right, so having defined paths, we can now say precisely what do we mean by a connected graph. Definition. A graph is connected if there is a path between every pair of distinct vertices. A graph is called connected if there is a path, at least one, between every pair of distinct vertices. So, I mean, we only care about distinct vertices. Can we get from one to the other? And we're not interested in loops here, right? In this definition, because you can just stay in the vertex and not go anywhere. That's kind of a trivial way to connect the vertex to itself. Here's an example. So if we look at the graph with 4 vertices and 3 edges, A, B, C, D are the vertices. So this one is connected. You can get from any vertex to any other vertex, and we can just list the corresponding paths to prove it, but it's clear from the picture. So this one is connected. But if we say have only 2 edges like this, with the same vertices, B, A, C, D, this one is disconnected. Right, because you cannot get from, for example, from vertex C to vertex B. There is no edge and no path. And visually, this is very easy to grasp, right? For small graphs, if I show you the picture, unless somehow I draw it in some way which will have many crossings, right? It might not be immediately easy to figure out whether it's connected or not. So you have to redraw it maybe and make sure that it looks something like this, where you have several disconnected parts. And so the next thing I'd like to formalize these disconnected parts. In this case, there are 2 disconnected parts. So they're small. It looks like a smaller, 2 smaller graphs, right? Each of which is connected. So if I just pay attention to the vertices C and D and forget about the rest of the vertices, they form a connected graph with 2 vertices. And same goes for the other 2 vertices, B and A. So this means that you can conjecture that in general, any disconnected graph will break into a collection of several graphs, each of which is a connected graph, but between themselves there are no connections. So such smaller graphs are called connected components. That's what I want to define next. I want to define it precisely. So please bear with me. I first need to define what do I mean by smaller graphs. That's useful in other problems as well. That's called a subgraph. So let G be graph. imagine removing some edges and vertices from G. Remove some vertices and some edges from G. Well, there have to be some consistency rule how you remove them. We should remove in such a way that if we remove a vertex, we should remove all edges ending on that vertex. In such a way that removing a vertex, we also remove all edges ending on it. Then what we obtain this smaller graph, which is called a subgraph. If we follow this single rule, we obtain a smaller graph. And H called a subgraph of G. So its vertices, the vertices of H, they form a subset of the set of vertices of G. And its edges form a sublist, a shorter list from the list of the edges of G. Okay. And in general, there are many ways to do it, to erase some vertices in some graphs. So any graph usually has several different subgraphs. So here's an example. Suppose I start with this graph, and the vertices I label as A, B, C in the middle, D, and E. That's my graph G. Here's an example of one subgraph. B, C, E. So I can call it H1. So what one needs to check is that, well, each vertex should be also a vertex of G. Right, and we see that G is gone completely, but we retain A, B, C, and E. And then each edge, which appears in H1, also appears in G. Right? Then it is a subgraph. So I call this one H1. There is also another one, just as an example, C, E, D, call it H2. That's another example of a subgraph for the same reason. But these are just examples. There are many more. You can draw them themselves, but just to give you an idea what subgraphs are, here are two examples. Okay, now we are ready to define formally a connected component. Definition: a connected component of a graph G is a subgraph of G that is connected. Is a subgraph of G that is connected but that is not contained in any larger connected subgraph. But is not contained in any larger connected subgraph. Any graph can be represented as a union of its connected components, which are disjoint. Let's write this as a fact or a theorem. Let's write this as a theorem. Any graph can be represented as a union of its connected components, which are disjoint. Disjoint means have no common edges and no common vertices. So in this example here, I have two connected components, CD with one edge and BA with one edge is the second one. But the condition on the having a maximum possible connection graph is important because I can sort of take even smaller subgraph. For example, just the vertex C without any edges. Just a single vertex is trivially a connected subgraph because the connectivity only, you need to check for distinct vertices, and there are none. So there is a smaller connected component, smaller connected subgraph, but it's not called a connected component, right? It must take as large as possible subgraph, which is connected to arrive to a connected component. Okay. And that's all for today.